Welcome to MATLAB school. In this video, we are going to simulate the MPPT for P&O MPPT for solar PV with a boost converter. The same model is available for download from the link given in the description. If you want, you can download it and you can use it for your purpose. Let us get into the simulation part. So this is the MPPT model that we are going to implement. This is P&O, Perturb and Observe type of MPPT that we are going to use now. So to implement that, we need to sense the voltage and current initially. So from the sensed voltage and current, we need to calculate the power. Okay. So the calculated power, the current power will be compared with the previous power. Okay. So P of t is the current power and P of t minus 1 is the previous power. If it is found to be, if the current power is found to be greater than the previous power, then we need to compare the voltage. Here we are comparing the voltage, current voltage with the previous voltage, and if the current voltage is found to be greater than the previous voltage, the pulse width will be incremented by a value of del D. Okay, and if the voltage is not found to be greater than the previous voltage, then we need to decrement the pulse width. In the other side, if the current power is less than the previous power, again we will be comparing the current voltage with the previous voltage, and if the current voltage is found to be greater than the previous voltage, we will be decrementing the pulse width. And at the same time, if the current voltage is found to be less than the previous voltage, we will be incrementing the pulse width. So del D is the small change in pulse width. So based on that, we will be implementing the MPPT. So let us look into the simulation. So this is the model that we have now, and this is the PV panel. So let me open this PV panel. So I have chosen this PV panel. You can see the maximum power of the single panel, then cells per module, open circuit voltage, short circuit voltage. So I have used an array. This array is having 5 parallel strings and 15 series strings. So we can plot the values of um, power, voltage and current with respect to the irradiation and the temperature. So here the temperature is 25 degrees C, and for other irradiation values 200, 400, 600, 800 and 1000, the values are simulated. Okay. So this is the plot across voltage and power. So 0.8 kilowatt per meter square. So this is the radiation. So this corresponds to 800 uh, watts per meter square of irradiation. Okay. So when the irradiation is 800 and the temperature is 25 degrees C, the maximum power that we can get out of the system is 22,649 watts. Okay. So and the corresponding voltage that we get is 733. So like that we have maximum powers available at different irradiation values. So when the irradiation value is 600, you can see the power decreasing to 16,964. Okay, so like that when the irradiation is 200, the maximum power that we can get out of the system is 5,490. So with this understanding, we are getting into the simulation. So when the irradiation is uh, 800, the value of power that we can, maximum power that we can get out of the array is 22,649 watts. Okay. So here we are giving irradiation value of 800 and temperature of 25. Okay, so irradiation is 800 and the temperature is 25. Okay, so for that the maximum power that we can get is to around uh, 20,000. Okay, 22,000. Okay, so here we are measuring the voltage and current, uh, and these are the plots. Okay, PV voltage, PV current, uh, and this is the load voltage and load current. So this is the load voltage, and this is the load current. Okay, so it is, this current will be measured and it will be displayed through the stack, and this voltage will be measured and it will be displayed through the stack. And if we multiply voltage and current, we'll be getting the power. So this is the output power at the PV panel, and this is the uh, power which is available at the load. Okay, so here we have the coding. Yes. So as I told you earlier, we are measuring the voltage and current, and this is the initial value of pulse width, and this is the maximum value of pulse width, and 0.001 is the minimum value of pulse width. And del D is a small change in pulse width. So if it has to be incremented, it will be incremented by a value of 0.00005, and if it has to be decremented, again it will be decremented by a value of 0.00005. Okay, and here we are doing some initializations. As I told you earlier, we are doing the comparison part. So this coding has been developed based on the flowchart that we have seen a bit earlier, and finally we'll be getting the uh, value of pulse width. Okay, right. So let us run the simulation and see the power output. Um, so here, as the load, I have a variable resistor, right? So this is the variable resistor, and to that resistor, we are giving three values. Initially, the value of the resistor would be 50 ohms for 3 seconds. Then later, the value will be changed to 100 ohms for again 3 seconds. And the resistance will be varied to 150 ohms for next 3 seconds. Okay, so gradually we are raising the load, and we are checking the power delivered to the load as well as the power supplied or extracted from the PV panel by means of this MPPT algorithm. Okay, let us run the simulation. So the simulation has started. Let us see the uh, PV panel voltage, current, and power. So this is the first graph is the PV panel's output voltage, second one is current, and third one is uh, power. So as you can see, we are almost getting the maximum power. So at when the time reaches 3 seconds, as you know, there is a change in load. So even if the load is increased, as you can see, there won't be any significant change in the current, I mean the power extracted from the PV panel. Okay, so you can see the current getting decreased to certain value, but that will be compensated by the increase in voltage. The simulation is running. Yes, now it is about to reach 6 seconds. So at sixth second, there will be a switching in load. So now the resistance, load resistance becomes 150 here. So here up to 3 seconds, the load will be 50 ohms. From 3 to 6, it will be 100 ohms. And from 6 to 9, the load resistance will be 150 ohms. So as you can see here, when we increase the load, the current decreases. So to compensate that, the voltage will be raised by the P&O algorithm, so that we will be getting the maximum current continuously from the PV panel. Okay. So this is the advantage of using MPPT technique in PV panel. So here we have inductor and a few capacitors. So we are using these capacitors and inductors just to boost the voltage so that the boost converter acts appropriately with respect to the incoming voltage and current. Let us see the load current. So, so with the implementation of this MPPT, you can see the current, uh, voltage and power getting transferred to the load. Okay, I see it has got hanged. Yes. So as you can see, uh, the current and the power, output power, the load power, which is almost reaching uh, 20,000 watts. Okay. So these models are available for download in the link given in the description. If you want, you can use it for your purpose. Okay. Yes. This is the PV panel's output, and this is the load current, load voltage, load current, and the power available at the load side. So as you can see clearly here, you can see the voltage current getting decreased as we increase the load, and I mean as the load resistance increases, you can see the current decreasing, and that will be compensated by the increase in voltage. Again, thanks for watching. Thank you.